All right, hello. My name is Ezra Kissel. I'm with Indiana University. Today I'll be presenting a collaborative project called EODN-IDMS, the Earth Observatory Depot Network, and IDMS, the Intelligent Data Movement Service, which is an instantiation of EODN running on GENI. The goal of this project is to provide a distributed storage service for open access to really all types of remote sensing data, but today we're going to be focusing on access to Landsat data for natural resources and educational applications. So the application that we're highlighting is called RealEarth. It is being developed by Dr. Sam Batzli, who is Director of WisconsinView at University of Wisconsin-Madison. And what we'll do is have Sam talk about his application and its use of Landsat data. And then I will go and talk a little bit about the details of EODN-IDMS and its the underlying infrastructure. And then we'll actually do a brief demonstration that will go over the workflow of a particular Landsat ingestion process and how it looks in RealEarth's application. So without further ado, I will hand it over to Sam, who will get us started.
The application that we're developing is called RealEarth, which comes from the concept of real-time data globally. What we're trying to do is bring together very different data sets, the kinds of data that meteorologists use and the kinds of data that land remote sensing researchers use. And we find that putting these together in a common visualization tool allows us to see patterns and discover relationships between what's happening on the land and what's happening in the atmosphere. EODN, we believe, is going to make RealEarth a better application by making the land imagery available faster. Using Landsat imagery for weather is not typical. It's generally used for looking at crop health or forests. And what we're doing here, though, is bringing it to meteorologists in their environment so that they can look at the relationships between the Earth and fog or wildfires and weather, cloud patterns, ice coverage, hail swaths, things that connect the land and the weather. Visualizing it together, we find that there's relationships that we may not have known about before. There's some inherent differences between the kinds of data that we're merging together here. Landsat data is generally available every 16 days, where there's weather data you can get every 15 minutes. The spatial resolution of Landsat imagery is 15 to 30 meters, whereas the weather data tends to be 1 kilometer or even 4 kilometer pixels. There are high latencies for the Landsat data. It takes a while to actually get a Landsat scene into your work environment. Low latencies for weather data. It streams into the weather applications sometimes within 30 minutes. The spatial coverage of Landsat data is a narrow 185 kilometer swath, whereas the atmospheric science weather satellite imagery will often be a whole hemispheric coverage, or a full disk, they sometimes call it. In the image on the left, you can see the detail available through the Landsat image of clouds. On the right, you see what a typical meteorology image would look like. And what's more important is the Landsat imagery was never intended to look at clouds, and so that would have been considered junk data. It would have been thrown away. But because it has value to meteorologists, we're thinking, why don't we bring this data to the meteorologist and see how it could be useful? So the problem is that the meteorologists need the data when it matters, and the Landsat imagery generally gets there too late the way it's developed now. So we're trying to reduce that latency. Part of the way we can do that is by bypassing this sort of shopping cart approach that is typical of land remote sensing data, define the locations of interest automatically, and stage that imagery near those locations where it can be quickly processed. Also, it will make it accessible to multiple applications, not just the land remote sensing community, but the atmospheric science community as well, which use different software stacks. One of the answers, or part of the answer here, is data logistics. And EODN is the Earth Observation Depot Network is going to help us move this data around more efficiently.
So we're working with the AmericaView community to address some of the concerns in accessing Landsat data that Sam just mentioned. And what we're trying to deploy is something called the Earth Observatory Depot Network, or EODN. And the idea is to provide open access to all types of remotely sensed data from a wide range of different sources, from public, private, and commercial. And right now, EODN is being deployed on a volunteer basis by different AmericaView members, and we can also make use of existing depot resources or storage resources that are in projects such as ReadyNet. The ultimate goal is to have a nationwide network of storage depots that can be used by the community to upload content, satellite imagery being the main usage that we're focusing on, do intelligent content distribution, and then provide this notion of geographic locality that supports application and researcher workflows so that they can reduce the latency to getting the data that they're interested in and reduce the time for acquisition in their workflows. So we are building EODN in part with the NSF-funded Data Logistics Toolkit, and the DLT provides sort of the software stack that's necessary for running the depot services and makes it easy to deploy with installable instructions so participants can go to a website, download the packages, and bring up a depot service that can be part of this broader network. The latest instantiation of EODN and using DLT is something we call the Intelligent Data Movement Service, or IDMS. And what we've done here is extend the EODN concept to work on GENI and use the GENI infrastructure. The nice thing about GENI is that we can make use of the dynamic and geographically diverse storage and networking resources that are available across the multiple GENI aggregates. And one of the nice features we can leverage is sort of the dynamic nature of the GENI control framework, where we can bring up the notion of ephemeral storage for scientists and applications that support their workflow for a given set of time or period of interest that really focuses on the type of content that they're interested in, make it available, allow them to do the processing necessary, and then we can dynamically destroy those resources again and make them available to the community. So the ability for EODN and IDMS specifically to make use of these dynamic resources is a key insight to our work. For today's demonstration, we're going to show a typical workflow of bringing Landsat data to the RealEarth application. And the way we do this is we typically have clients register or subscribe to scene data or imagery data that they're interested in. And we, at the moment, have a client here in the demo room, a laptop, our GEC22 host, which is going to subscribe to scene data that's of interest. So we use our UNIS information store to be notified when the scene data is available. At the same time, we're constantly harvesting new scene data from the Landsat ground network. And we have a harvester node at Indiana University in Bloomington that's constantly staging this sensing data or the scene data into the EODN-IDMS GENI. Since we're on the East Coast, we want to be able to stage our sensing data locally to reduce the latency and time it takes to actually download the data. So we're going to be using storage resources on GENI that are close to the DC area or on the East Coast. So the pool of depots we're going to use start in Rensselaer in North Carolina, going up to the Max Gigapop, which is close to College Park, Maryland, across the river, and NYSERNet in New York, and Cambridge in Massachusetts at the GPO. Now that we have our scene data staged where we'd like it, we actually have the harvester send a publish message to our information service, which generates an event to our client that allows us to initiate the fast download from the local storage resources. At that point, the local host here can do processing and transform the raw satellite imagery into a format that's useful for the RealEarth application. So we upload that data to the RealEarth service running at University of Wisconsin. And now what we'll do is bring up some web interfaces to show you how the typical workflow looks in terms of reporting the download progress and showing some usage. At this point, we have a workflow running, and I'm taking you now to this screen, which shows our depot status page. And we're able to track all of the active depots in the EODN-IDMS service. We can see that we have a number of registered depots that are actively being used. And what we can do is bring up charts to display various collected metrics. And since we have our workflow script running, we should start seeing some movement in these charts. So here we're actually looking at the NYSERNet depot, one of the storage resources that we're using on GENI. And as the workflow script is staging the data, you can see that the usage is now going up on this chart. And we can also track the system utilization, which obviously tells you that something is happening on that storage resource. You can see active downloads that are being processed by the workflow. So here we have a bunch of scene data that's being downloaded, and we're able to select certain scene files and visualize their progress as they're coming down from the different depots that we've staged the data at. So at some point, we're going to get a large file. These, as you can see, there are many small files within a particular Landsat scene. The Landsat data that we're interested in downloading are these 1 gigabyte files, and you can see that a couple of them just showed up. And unfortunately, due to some hotel network logistics regarding the network, we have to do the actual download from our host at IU, but we can demonstrate the same type of performance difference between these two downloads. So here we have a scene that is interesting to RealEarth, and it's being downloaded quite quickly because we staged it at depots that are closer to our download point now in Indiana. Whereas we have this sample file called My Big Data that's been staged sort of randomly at depot locations throughout the US, and you can see the download rate is much slower. In this case, about over twice as slow as the one where we've intelligently staged data that will drive the RealEarth visualization. So at this point, the workflow is being sent to RealEarth, and now I'll turn it back over to Sam, who will be able to show it in his application.
Thanks, Ezra. So what we're looking at now is the browser interface for RealEarth, and what it's showing is some typical meteorology imagery. We have radar on top of infrared satellite imagery. But what I want to show you now is how we brought the imagery that we just uploaded from here to the Wisconsin server where the RealEarth application resides, and this is the two satellite images that we uploaded, and it's a 2013 image of the rim fire in Yosemite National Park. And what's important about this is we're able to bring this imagery during the course of this demo from the USGS source right into our application here. And the reason it matters is because the kind of view we can get of a wildfire using land remote sensing imagery is quite different than what we would see with the typical meteorology imagery. In this case, when we enhance it and zoom in, we see the actual fire burning. And this can be very helpful for those who are concerned with how the wind might be affecting the fire, and gives us a new way to look at weather and land interactions.
So to wrap up our demonstration, I just want to say that today, GENI is allowing us with EODN-IDMS to enable on-demand local storage acting as these fast caches for time-sensitive data. And we've demonstrated how we can reduce the time to acquire and expose new high-resolution map data for RealEarth users. And Sam has definitely shown the usage of this data in a compelling and interesting use case. And I also want to mention that we really have developed sort of a shared vision with driving this rapid development and cross-collaboration between the various projects that we've been involved in. So the work with GENI and IDMS has really pushed the development of the DLT infrastructure and is really allowing us to make the EODN infrastructure happen as well. So the overall goal is to eventually have a prototype, a functional long-lived service that benefits the remote sensing community as a whole. And in the future, some of the things we'd like to enable is to also upload and publish some of the processed data sets. For instance, the imagery that RealEarth is using could be of benefit to the community as a whole. So EODN also allows us to push that data back into the depot network, register metadata about it, and allow the other users of EODN to basically make good use of what's already been processed and reduce duplicated effort, in other words. The other thing is we definitely want to do our complete tighter integration with existing and widely used map-based browsers. There's been a lot of effort in the USGS community to have very compelling interfaces for finding the imagery that you're interested in, and we're working closely with those development teams to try to merge together our system with what already exists and what other users are already comfortable with. So if they can find the image data that they're interested in, the scene data that makes their application run, but now they have a way to use EODN to get faster access to that data, then everyone wins. So I will just have a thank you slide here. There's a few links and our contact information. We'd like to thank our support from the NSF, our CCNI grant in developing DLT. And finally, let me take this opportunity to thank our behind-the-scenes team from Indiana University. We have Akshay, Jeremy, and Prakash. They've all worked really hard in developing the back end for EODN-IDMS and to really bring this demonstration together. So thank you all. Mm-hmm.